Imagine you are building a social media app. A user opens the app, scrolls the feed, likes a post. Behind the scenes, the backend has to fetch sessions, update counters, or check rate limits, and store temporary data. Now imagine millions of concurrent users doing this simultaneously. If every request hits your database, the system quickly becomes slow. That's why many companies like Twitter, Instagram, Uber rely heavily on a technology called Redis. Redis can handle hundreds of thousands of requests per second with extremely low latency. But here's the surprising part. Redis is mostly single-threaded. So how can a single-threaded outperform a complex multi-threaded systems? To understand that, we need to explore the architecture of Redis. Let's start by understanding why traditional databases become slow. Imagine a database like MySQL or PostgreSQL. When many clients connect, the database often creates multiple threads to handle them. So the architecture looks something like the client connects to a thread, then the query is made, and then disk operations are performed. Now, this introduces several performance problems. First is the context switching between threads. Second one is the logs because multiple threads may try to modify the same data. And the third and the biggest bottleneck is the disk access. Accessing disk storage takes milliseconds, but modern CPUs operate in nanoseconds. So that difference is enormous. To understand why Redis is fast, we need to understand something called memory hierarchy. At the top, we have CPU cache, which is incredibly fast. Below that is RAM, where Redis stores its data. And then we have SSDs or disk storage, which traditional databases rely on heavily. RAM access takes roughly hundreds of nanoseconds. Disk access can take milliseconds. That difference might sound small, but in computing, it's enormous. Accessing RAM is like walking across the room. Accessing disk is like flying across the world. So Redis simply avoids the slow part. Now, storing data in RAM definitely makes Redis fast, but RAM alone does not explain how Redis handles thousands of requests simultaneously. Imagine a popular application like Instagram or Twitter. At any moment, thousands of clients may be connected to the server, each sending requests. Each of these clients communicate with the server using TCP connections. Every time a client connects to Redis, it establishes a TCP connection. So if we have thousands of users connected, Redis may have thousands of open sockets. Now here comes the challenge. A naive way to handle this would be to create one thread for each client connection. But if Redis creates thousands of threads, the CPU would spend a lot of time switching between these threads instead of doing useful work. This process is called context switching, and it becomes extremely expensive at scale. So instead of creating thousands of threads, Redis uses something much smarter. It relies on a mechanism called IO multiplexing. On Linux system, this is implemented using epoll. Epoll allows Redis to monitor thousands of network sockets at the same time. Epoll is like a teacher watching a classroom. Instead of asking every student one by one if they have a question, the teacher simply looks for raised hands. So that's kind of a mechanism that Epoll follows. In operating system, every network socket is represented by something called a file descriptor. epoll continuously watches these file descriptors and waits for events. Whenever a socket becomes ready for reading or writing, epoll notifies Redis. So instead of constantly checking every connection, Redis only processes the connections that are ready. This allows Redis to handle thousands of concurrent connections using a very small number of system resources. And these ready requests are then passed to the Redis event loop which processes them one by one. But that leads to another interesting question. If Redis processes requests one at a time using a single thread, how does it still remain so incredibly fast? In the previous section, we saw how Redis uses epoll to monitor thousands of client connections efficiently. But that still leaves us with an important question. If Redis handles all these requests using just a single thread, how does it still remain so incredibly fast? The answer lies in the Redis event loop. At the heart of Redis lies the event loop. You can think of event loop as a continuously running loop that waits for incoming requests and process them. Whenever epoll detects that a client socket is ready, that request is passed into the event loop. When a request arrives, the command from the client plays into the command queue. For example, a client may send commands like get the user having ID 123, set the session as ABC, or increment the likes on a post. These commands are added to the queue waiting to be processed. The event loop then processes commands from the queue one by one and executes them. Because Redis stores its data in memory, these operations are extremely fast. Most commands complete in microseconds. Now, this might sound counterintuitive. We often think that using multiple threads improve performance, but Redis intentionally keep its core single-threaded, and this design decision turns out to be a huge advantage. Since only one thread modifies the data structure, Redis never needs logs. In multi-threaded systems, threads often compete for shared resources that require synchronization mechanisms like mutexes or logs to prevent data corruption. But logs introduce overhead and complexity. Redis completely avoids this problem. Another major performance cost in multi-thread systems is context switching. The CPU constantly switches between threads, saving and storing execution states. This process can become expensive when thousands of threads are running. But Redis avoids this overhead entirely because only one thread executes the commands. So Redis combines efficient networking from epoll with a simple single-threaded event loop. Thousands of client requests arrive, they are placed into the command queue, and the event loop executes them extremely efficiently in sequence. This simple architecture turns out to be incredibly powerful for workloads involving lots of small operations. For example, imagine a social media app updating the number of likes on a post. Redis simply executes a command like increment post likes. Because this operation happens entirely in memory and without logs, it completes extremely quickly. But there is another important reason Redis commands execute so quickly, and that comes from the specialized data structures used internally by Redis. Here comes the specialized data structures Redis uses internally. Redis is often described as a simple key value store, but internally it is actually a data structure server. Instead of storing plain values, Redis stores optimized data structures directly in memory. These include strings, hashes, lists, sets, and sorted sets. Let's start with the most basic type, strings. Redis does not use regular C strings internally. Instead, it uses a custom structure called SDS, Simple Dynamic Strings. Unlike normal strings, SDS keeps track of the current length, the free space for future expansion. This allows Redis to perform operations like getting string length in O of one time. For example, get username. Redis can return the value almost instantly. Next, we have hashes. Internally, Redis implements hashes using hash tables. Imagine storing user profiles using a command set user colon 100, name as Alice, and so on. Hash tables allow Redis to look up field in constant time. Redis sets are collection of unique elements. Internally, they are implemented using hash tables as well. For example, followers might store the ID of users following someone. Redis lists allow efficient insertion at both the ends. They are commonly used for things like queues or message pipelines. For example, pushing a job one in a queue from the left side. Many background job systems use lists to manage tasks. This is the most interesting one. One of the most powerful Redis data structures is the sorted sets. Internally, Redis uses something called skip list. A skip list is like a layered linked list that allows Redis to search elements much faster. This is perfect for things like leaderboards. Redis can instantly answer questions like who are the top 10 players. Because Redis uses these optimized structures, most operations have extremely low latency. Many commands run in constant time. Even more complex operations like sorted ranking only take logarithmic time. So, Redis combines three powerful ideas. First, all data lives in memory. Second, a simple event driven architecture. And third, highly optimized internal data structures. When these three come together, Redis can process hundreds of thousands of operations per second. But Redis is not just fast, it also needs to make sure data is not lost. So the final piece of Redis architecture involves persistence mechanisms like snapshot and append only locks. Memory is extremely fast, but it's also volatile. If the machine shuts down, the data stored in the RAM disappears. To solve this problem, Redis uses persistence mechanisms that periodically save data to the disk. Instead of blocking the main server, Redis creates a background process using the fork system call. Fork creates a child process that is an exact copy of the Redis process in memory. The main Redis server continues serving requests while the background process safely writes data to disk. This allows Redis to maintain high performance without blocking client requests. So the first persistence method is RDB snapshots. At specific intervals, Redis saves the entire dataset to disk as a snapshot. Suppose every 5 minutes or after X writes. Think of it like taking a photo of the database at a particular moment in time. If the server crashes, Redis can simply reload the most recent snapshot. The second persistent method is called the append only file or AOF. Instead of saving the whole dataset, Redis records every write command executed by the server. For example, capturing the user information of a user or incrementing likes on a post. When Redis restarts, it can replay these commands to reconstruct the dataset. It works like a transaction log in traditional databases. Each approach has a different advantages. RDB is preferable for small files and faster recovery, while AOS is having more durability and less data loss. Many production systems actually use both together. So, this design allows Redis to combine the best of both worlds. In-memory speed, efficient event-driven architecture, optimized data structures, safe persistence to disk. This is why Redis is able to process hundreds of thousands of operations per second while still maintaining reliability. What looks like a simple key value store is actually a carefully engineered system optimized for performance. Redis is not just fast because it runs in memory, it's fast because every layer of its architecture is designed for speed. If you enjoyed this deep dive, consider subscribing. I am planning more videos breaking down how real world systems are built under the hood. Thanks for watching. Bye.